Good afternoon. Welcome to today's talk in the CrySP speaker series on privacy. Our speaker today is Professor Asokan. He's a professor of computer science and engineering at Aalto University and a professor of computer science at the University of Helsinki. He got his bachelor in computer science engineering from IIT Kharagpur, his master's in information science from Syracuse University, and his PhD in computer science from the University of Waterloo, so he's one of us. After getting his PhD, he spent 17 years in industrial research. He worked at the IBM Zurich Research Laboratory and then at Nokia Research Center. He's an associate editor of ACM TISSEC, and he also serves on the steering committee for ACM WISEC. His primary research interest has been in applying cryptographic techniques to design secure protocols for distributed systems. Recently, he has been focusing on security for mobile devices and users. And last but not least, considering that this is the CrySP speaker series on privacy, I think it's worthwhile pointing out that the very first paper written by him was about untraceability in mobile networks back in 1995. And so that probably makes him the person who has been working the longest on privacy in this room. Does anyone want to challenge this? Maybe yeah. 1995. Okay, let's introduce him.
Thanks. Thanks, sir. Like I said, in addition to being a student, I also used to work here in the building over there. One of my former colleagues used to say we did time over there. So I did 6 years of time in the in the math building over there. And I remember, so I was working for MFCF, and Ian was in the computer science club. And whenever he gets bored, he will look at some man page of some program that is administered by MFCF, find a way to break it, and he'll come stomping down the corridor. So whenever I hear the footsteps, I know that something has been broken and we have to rush to fix it. But he was always had responsible disclosure. He told us before he publicized everywhere else. Okay, so it's always a pleasure to come back. It seems I'm coming back at the rate of every 5 or 6 years since I left. I'm going to talk about today on some work that we are doing on mobile malware. So I've been doing mobile-related stuff before, but haven't really done anything with malware until about 4 or 5 months ago. So what I'm going to tell you is sort of what we found out. So we don't have a long track record in doing malware-related work. And this is joint work with my colleagues at the University of Helsinki and Adam Oliner, who's at Berkeley. I'm sure you have all heard that mobile malware is a big problem that's waiting to happen. And we have been hearing this story for a while. So I did this search with different settings. So this is like as of, was it 2006? And there were already warnings about mobile malware. And the warnings have sort of continued until recently. On the other hand, I think it seems to have run out of battery, so I'll stand here and this. So on the other hand, research, even though academic researchers have been interested in mobile security and mobile malware as such, the research has been focused primarily on analyzing applications and trying to detect if they are malware or not. No one seems to have worked at estimating how bad is the problem really, how much more mobile malware is out there in the wild infecting real user devices. So the only information that you find, so typically you hear about how many new malware samples are being discovered every year and how that's growing exponentially, but not really about what's the actual infection rate. So there are a couple of reports here and there. So this is from earlier this year from an antivirus company called NQ Mobile. And they claim that about 32 million devices were infected during the past year. And I think this was around the time when the Android install base was less than 1 billion. So this works out to about 5% infection rate. Another antivirus company had a more conservative estimate. I think this works out something like 2% infection rate in different categories. But these are all antivirus companies that are estimating what's the infection rate. On the other hand, the only independent estimate that I know of was a paper by people in Georgia Tech. And Urs just told me that Patrick Traynor was here a couple of months ago, so some of you probably listened to his talk. They were the only ones who had an independent estimate of infection rate among mobile devices as such, and they came up with a number of something like 9 out of 1 million. They had an indirect way of estimating infection, so they had large traces from a mobile operator and an ISP in the US, and they tried to look for queries to known bad host names and try to infer that as being coming from an infected device. So the question is, what accounts for this disparity? On the one hand, you have something like 9 out of 1 million. On the other hand, you have something like 4%. So what our plan was, can we actually verify this independently by getting data directly from the devices, unlike what the Georgia Tech people did, which is an indirect estimate. So we wanted to be able to get data directly from the devices to estimate infection rate. And then if we have this data, we could maybe go one step further and try to see what factors correlate with infection. And if you can measure these factors cheaply enough, we might be able to actually predict infection even before it happens. So this is our plan, and that we haven't really done all of this, but I'll tell you how far we got and what we found out. So the first step was to sort of get realistic data directly from devices. So of course, to get data, we have to figure out what kind of data we want. So the way we want to go about estimating infection rate is simply by identifying a software package on a device, and check for the presence of those packages in known malware databases. So every malware vendor has a database of known malware packages that they have discovered up to that point. So how do we identify an Android package? So if you look at the structure of an Android package, there is a manifest file, which has things like Java-style package name, like this one here, and a version code. But this alone is not a reliable package identifier, because there's nobody enforcing that these are unique. So within a device would ensure that there's only one package with that particular name. Also within certain markets like Google Play, Google will enforce that there's only one package with a given name. But there's no other way to enforce this. So nothing stops me from creating a package called com.facebook.katana, which is the Facebook Android package, and distributing it to whoever is gullible enough to install that. And this actually happens. A popular way of a popular technique for malware authors is to take well-known packages and modify it so that they actually have a malware payload in there, and then distribute it, hoping to fool people to install these well-known packages. On the other hand, every package also has a signature file attached to it. So all Android packages are required to be signed. And the signature is with respect to a developer-specific key pair. So normally there is no certification infrastructure or anything like that. So these packages are self-signed by the developers themselves. But because they are signatures, the certificates are statistically unique. So if you have a certificate, it's unlikely that I will be able to find a certificate or create a key pair that would match your key. So the combination of including this device, the developer certificate with the package name could give us a way to uniquely identify a package. So we thought of two ways of identifying it, and one is to just look at the developer certificate alone. And the intuition is that if I have a developer certificate that was identified in a malware database, then there's really no reason to trust that developer certificate anymore. If I sign some package that's malware, then probably that developer certificate is suspect, and therefore it would be safe to just count everything that's signed with respect to that developer certificate as potentially dangerous. So that would be one way, and then of course that might lead to certain misclassifications, false positives, but we thought that this would give an upper bound for infections. The other possibility is not only look at the developer certificate, but also a package name and the version code. So we look, given a package, we would look in a malware database to see, is there an entry in the malware database with the same developer certificate, the same package name, and the same version code? And then this could give us a lower bound for infections. OK, so we got 3 malware datasets from 3 different sources. Mobile Sandbox is a university project in Germany. And it's a sort of a community-sourced collection. So anyone can submit a package, and they would run a number of antivirus tools, I think something like 45 different tools. And if any of them identify that package as malware, they'll put it in their database. And they are the largest largest malware database that we found. So altogether, there were something like 16,000 distinct packages. McAfee gave us something like 3,000 malware packages that were the most frequent according to their measurements. Malware Genome is a project from the US, North Carolina, I think. And their collection was a kind of one-time collection that was made a couple of years ago. They had about 1,000 packages, but it was dated. It was a couple of years ago. So we had these 3 sources of malware data sets. And now we need to get this a way to get data directly from a large number of devices so that we can measure whether that device is infected or not. So in order to do this, we need a package that is reasonably widely installed. Some of my colleagues and their collaborators in Berkeley had actually a package like that called Carrot. So Carrot is an application that tries to measure average battery life on a device, and it reports the average battery life plus a number of the set of applications that are installed on the device. And they get this data from a large number of devices and analyze them so that they can pinpoint the battery usage that's caused by a given application. They actually got quite a bit of press coverage. For example, when there was this hurricane in the East Coast, I think they got coverage in CNN because that would be one way to extend your battery life by installing this application, and that will tell you which applications are battery hogs. And if you kill the battery hogs, your battery would last longer until you get power back. So because of this publicity they got, they had a large number of users. I think at last count they had 600,000 users altogether. So we thought that, and they would let us piggyback stuff on their application. So we thought we would use Carrot as a way to measure these unique identifiers from this large number of devices and can identify potential infection. So like I said, the Carrot data set consists of essentially it's time series data. So for every device reports the set of applications it has at different times. So each line there is a report from a given device, and the report consists of the identities of the software packages that are installed that are actually running on the device at any given time. So for different devices, you get at different points of time. Whenever the user runs the application, or whenever the application has something interesting to report, it reports it to the backend Carrot server. So initially, they were only measuring the package name because they were not interested in, they were not interested in security as such. The modification that we made was to add these developer certificates so that we have this reliable, unique identifiers for packages. So essentially, from every device, whenever every device reports the set of applications, we get this tuple of developer certificate, package name, and version code for each application. So we had collected data from March till about October, and we had something like 55,000 devices. So even though they have 600,000 users, about half of these are Android users. Not everyone has this new version that we pushed because they get a new version whenever they update to the new version of the package. So we had about 55,000 of the users who had upgraded to our version, which measures this developer certificates, package name, and version code. So that's the actual data set. And once you have this, then measuring malware infection was fairly straightforward. So basically, we have a malware data set. And if any package on a device was found in the malware data set, we label that device as infected. And if no match was found in any of the samples that were reported from that device, we label it as clean. So we don't actually distinguish between these different reports that come at different times. We just take them as a pool of applications for a given device over this 6-month period. And if there was ever a malware application found on the device, we label that as infected. So you can see here that the overall infection rates that we found. So the two things that I wanted to point out here. So one is that the bottom line, you see the infection rate. So that says that according to the Mobile Sandbox malware database, out of these 55,154 devices were found to be infected. And with McAfee, it was 144. With the third data set, we found no infected devices because that was an old data set. That's a kind of a reassuring thing that it seems like after 2 years, the 2-year-old mobile malware isn't found in the wild. So either people are removing them or they are using antivirus tools that actually eventually find those packages and remove them. But the interesting things are, first of all, you can see that between the Mobile Sandbox and McAfee, there is actually hardly any overlap. So there were 154 devices found to be infected according to Mobile Sandbox and 144 according to McAfee. But the total was 280. Well, if you consider the union, it was 285. So there were only something like 13 devices that were common to these two. Yes?
Do you know how Carrot identifies a device?
Carrot,
Self-reported?
right. So Carrot creates what's called a Carrot identifier. Whenever you install a Carrot application on a device, it creates a Carrot identifier using the IMEI of the device. I think they take all the identifiers that are possible and put it through a one-way hash function, including the current time. So if you reinstall Carrot on the same device, you will get a different Carrot identifier. But as long as you have the same installation, you have a unique identifier which can't be linked back to any other identifier. So that's how we inherit that identification as well. So we'll come back to this lack of intersection between these two data sets. The other thing to notice, which I also discussed a bit more, is the difference between the last two rows. So if you remember, the last row was this exact match. We look at the developer certificate, the package name, and the version code. And if you look at all of these three, then you get infection rates in the order of 0.28% or 0.26%. But if you only look at device certificates, developer certificates, the infection rates are much higher, and they're clearly too high to be really true. So we have something like 34% of the devices are supposedly infected. In other words, what this means is that 34% of the devices had at least one package signed with a developer certificate that had also signed potentially some other package found in a malware database. And this was initially for us counterintuitive because it looked like this assumption that we first made, that is, if you ever find a developer certificate in a malware database, then there's no reason to trust this developer certificate anymore, because clearly if you signed malware once, you probably are either you don't have good care, you don't take good care of your signing key, or you are yourself a malware developer. And therefore, we thought it would be reasonable to discount any package, or at least to be suspicious of any package that was signed with the same key. And that's clearly not the case here. So, and this one makes the same point again. So this is for each data set, we show the different distinct certificates that are found on the different packages that are found on the x-axis, and on the y-axis we see these number of devices that were found to be infected using these two different methods. And you can see this big gap between if you use only DC developer certificate matching or if you use this exact matching. So we looked around a bit further to figure out why there was this discrepancy. So this one again shows this same thing in a different way. So on the x-axis you see distinct developer certificates, and on the y-axis you see the number of different packages that were signed with this given developer certificate. And you show both malware packages that were signed with the given certificate and all packages that were signed with the different given certificate. And you can see that for a large number of these developer certificates, they sign both malware and non-malware. And this is the reason why we find this large number of matches if you use this developer certificate only method. And there seem to be a couple of reasons for this. One is that there are keys that are well known. So for example, the Android open source project comes with a test key, which is meant as a kind of, if you are debugging something or if you're trying something out, you would use that key. People use this to sign packages, which are actually found in Google Play. So malware developers use this as well, and that perhaps you could understand because they want to sign with a key that cannot be traced back to them. But 4 times as many packages, inner course packages were signed with the same key. And this, of course, makes that initial assumption pretty much useless. So that's one reason. And the second reason is, even otherwise, people seem to use the same key to sign malware and non-malware. So for example, we found one case, which is an application which is quite popular called Brightest Flashlight. Apparently, version 17 was detected as malware by several antivirus tools. And presumably, this is because they all use ad packages, ad libraries. And some ad library that they used had a malicious payload. So lots of antivirus vendors labeled the whole package as malware because whatever library you use will inherit, the code in the library will inherit the permissions that are given to the application. So the developers, of course, scrambled to fix that. But they still had an incentive to keep using the same signing key because of the way Android works. So in Android, if you have a new version of a package, that can access the data that belongs to the old version of the package if they were both signed with the same key. So if you change your signing key, then you have to have some way of arranging so that all your subscribers, all your users have some way of migrating their data from the old version to the new version. It's much simpler to just say we'll issue a new version which has the same signing key, and it continues to have access to all the data that the old version had. But so that's another reason why we cannot just look at the developer certificate, because even a legitimate developer has an incentive to keep using the same key even though one version was detected as malware. And there seem to be also other trends. So for example, we have seen ads where people want to buy your developer certificate if you have built up a certain good reputation because they can deliver payload using this, and they will give you good money for this. So again, you will run into this case where you have the same key that signed good packages for up to a period, and then suddenly starts signing malicious packages. So this is the reason why there's this discrepancy, and then it was clear that we cannot use this DC only matching. We have to look at the exact match, even though that might lead to an underestimate. The second issue was, if you remember, we had this 2 malware data sets, and they both, if you use the labeling by each of these data sets, we arrive at roughly the same number of devices as being infected, but there were very few devices common to them. And that sort of hints that there is no common agreement about what exactly constitutes malware. So this list shows some of the most frequent malware that we found in our data set. And one reason why there is disagreement about what's malware or not is the reason why somebody classifies a certain package as being malware. And the most common reason is adware. If something has, if a package uses ad library that is either privacy invasive or downright malicious, they will label that as malware. Different antivirus companies seem to have different levels of tolerance about how much of adware is considered to be bad. So this is one set of reasons for the discrepancy. Another one is things like, for example, the first application there is a monitoring application. So this is the application where you install it on your device. It can report what the device does, like the calls you make or the messages that you get, and so on, to some central, some entity outside the device. So it's like a monitoring service. And some of them market this, some of the developers market this as for example, as a child protection measure, that you install this on your child's mobile device, and then you can make sure that your child is not either intentionally doing something or not accidentally falling victim to some kind of scam. So again, antivirus companies seem to have different opinions about whether to consider monitoring tools as malware or not. Another set is routing applications that will turn your device into a rooted device. So again, I mean, if you installed a routing application yourself, clearly that's not malware. But if a routing application was installed on your device without your knowledge because you installed some other application and that pulled a second application, then that would be malware. So this seems to be one reason why there is disagreement about malware. And this disagreement is actually quite drastic. So this column says the number of antivirus tools that labeled each of these applications as malware. And there were total about 45 different antivirus tools. And as you can see, none of these were found as malware by a majority of the antivirus tools. So there is a clear disagreement here. And we can actually see that also in our original data set. So between the McAfee and Mobile Sandbox, just looking at the malware samples itself, the overlap was quite small. Between the genome data set had something, a more even distribution with the other two data sets. But again, there was what you would expect, or what we thought in the beginning was that there will be a large overlap among different antivirus tools, and there will be some outliers, but there would be common agreement, and this is clearly not the case. So, and because of this, it became clear that it doesn't make sense for us to combine these data sets and try to measure infection rates based on the union of these malware data sets, but rather we should actually treat each data set differently. And basically say every malware vendor has some way of labeling malware. And when we are going to talk about infection rates, or more importantly, when we are trying to do any kind of predictions, that should be with respect to that specific labeling algorithm. It doesn't make sense to combine two malware data sets from two different sources because they both have different ways of identifying malware. This disagreement is actually rather surprising because it seems like malware vendors do pay attention to other malware vendors. So they have the labeling algorithm that a malware vendor uses takes many inputs. One of them is their own analysis, but they also monitor what other malware vendors do. And as soon as some malware vendor classifies an application as malware, every other malware vendor takes this into account in their algorithm that does the labeling. And sometimes this leads to kind of a snowballing effect, that when somebody falsely identifies something as malware, and all the others also end up identifying it as malware, and this can go on undetected for a long time. And we actually had a case like this, which corresponded to an application that Google themselves released a couple of years ago. So a couple of years ago, the malware problem on Android was really bad. At some point, Google decided that they're going to publish an application called the Google Security Tool that would essentially serve as an antivirus application that would remove all the known malware. So as you can imagine, the day after Google published this, about 3 or 4 different hacker groups also published an application with the same name, supposedly signed with Google's key, and publicized as much as possible so that unsuspecting users would install that, and that carried a malware payload. So this, the second one, the malicious versions of this application was quickly flagged as malware by a large number of users. So this one is actually signed by this test key, and I think today about 20 antivirus tools detect this as malware. Again, notice that it's only 20. Even though this is clearly malware, only 20 of the antivirus tools actually detect it as malware. But in this happened in the space of like a couple of days. And in the rush, somebody actually ended up detecting the original Google's version as malware as well. And even today, if you go to VirusTotal, which is a service that lets you see whether an application is malware and how many different tools rate it as malware, the Google signed version is identified as malware by 13 different antivirus tools, including some very popular ones like McAfee and Trend Micro and so on. The reason why this is not hasn't been noticed and hasn't caused any kind of has stayed undetected is because we didn't detect any of this either of these packages in any devices that that we found, because this is like something that happened a couple of years ago, and both the malware version and the non-malware version are not in use anymore. But this is a direct effect of antivirus vendors watching at how other antivirus vendors do their classification and taking that as part of their own method of labeling malware. So given this, it's surprising that there is still such a big disagreement among malware vendors, even though they actually pay attention to each other. So while we are doing this, we also thought that we can use the same mechanism actually to measure market share of antivirus tools. Just like we detect malware, we can also take the antivirus tools themselves and look for their signature and version number and package name. Maybe the interesting thing here is that there's actually a big difference between malware tools and the ones that are well known in the PC world, like Trend Micro and, for example, F-Secure is not even listed here. Some of them don't seem to have any presence in the mobile space, whereas the most popular mobile antivirus tool is Lookout, which is primarily a mobile antivirus company. Okay, so having done this, collected this data, and the main result there was the infection rate that we found. First of all, one cannot talk about infection rate in general. The infection rate depends on how is malware classified, and we saw that the classification differs from malware vendor to malware vendor. But whichever classification that we tried, the infection rate seemed to be substantially higher than the previous independent estimate from Georgia Tech. So it's not 9 out of a million, but it's something like 2 out of 1,000. So now that having got this data, we thought, can we go one step further and try to use it to predict the likelihood of infection? So in particular, we now know that we cannot talk about this. So if you're going to predict likelihood of infection, we have to actually do it separately for each malware data set, because there is no common agreement about what constitutes malware. So we looked at different factors. So one is that because Carrot has this average battery life, we tried to see if there is difference in average battery life between clean devices and infected devices, again, separately for Mobile Sandbox and McAfee. And it seems like there is a difference, that clean devices have, in general, longer battery life than infected devices, but the difference is not really significant. So in the case of Mobile Sandbox, it was significant, but in the case of McAfee, the difference is not significant. So this cannot really be used as a factor if, well, it may be possible to use it as a factor, but we have to be careful about the fact that it's not a definite indicator. Similarly, we looked at the number of packages. So is there a difference between the number of installed packages between infected devices and clean devices? And again, it was the same thing, that there seemed to be a difference, but it was significant in one case, not in the other case, except that now it was reversed. In the case of McAfee, it was significant. So clean devices had fewer installed packages on the device on average than infected devices. In the case of Mobile Sandbox, it seemed to be lower, but the difference is not significant. So the next thing we did was, so if you remember, the way Carrot collects data is basically the set of applications that are installed on the device. So our intuition was that the set of applications that you have running on your device is probably indicative of your behavior, right? So if you go to certain app stores, the set of applications on your device might reflect that. And then it was known or suspected that some app stores have much more malware than other app stores. So Google takes care of the app store. They try to keep up with, they have in the intake process, if they detect malware, they throw it out. They also periodically scan for malware. But other app stores may be in different countries, or maybe different sort of thematic app stores. There is a porn app store, or there's some other specialty app store, and they tend to have a bigger malware concentration. So we thought that if the set of applications can be a proxy for user behavior in general, and specifically things like which app store that you go to. Then by looking at this set of applications that you have, like non-malware applications, we might be able to predict whether your device becomes infected at a later point of time. So essentially the question of, can the list of applications on the device predict susceptibility? And this is kind of like this old saying that your friends, looking at your friends, you can infer something about yourself. So the company you keep tells something about yourself. So we wanted to see if this actually holds true. So the way we did that, first of all, we wanted to see if this is really even a promising avenue. So basically, we divided this set of applications. So we use this all the malware data set that we have to label the applications, and just doing a simple 5-fold classification. Training with 80% of the data, 80% of the devices, and then see if we can predict the labeling of the devices as clean and unaffected on the remaining 20%. And as you can see, the precision is rather low. This is not what you would what would be acceptable in any normal classification scenario, but it's still better than the baseline. So in the case of mobile sandbox, the actual infection rate is 0.28%, but this classification would identify a pool of devices infected, out of which a higher fraction than 0.28% is infected. So in other words, compared to a random sampling, this classification is about 5 times better. So and the number was somehow similar for McAfee as well. So normally this wouldn't be, like I said, this wouldn't be good enough. The precision is too low. But there are 2 things that's worth noting. One is that this instrumentation comes very cheaply. We are simply collecting the set of applications that are installed on the device, and that doesn't really cost anything. In the case of Carrot, this is reported anyway, but it doesn't add to the energy cost or anything like that. So would we be able to use this rather cheap indicator not as a way of identifying infection? Because especially if you are talking about known malware, then what antivirus tools do is already good enough, right? So they look for signature matches. So rather than look at trying to replace anti-malware tools, can we do something else? So can we, for example, given a device, you can run an anti-malware tool to find out all known malware, and after you have removed them, you are left with supposedly a set of clean applications. And would this classification then help us find out if among the remaining supposedly clean devices, if some devices are more likely to be infected? If so, then anti-malware vendors could actually look at those devices more closely. So they can take all the applications on those devices and run static analysis or more expensive and in-depth analysis to find out if there is any previously unknown malware among those devices. So this is what, so we wanted to position this not as a way of replacing malware, but as a way of helping anti-malware vendors find previously unknown malware. So in order to do this, so again, for that case, the baseline or the computation is random selection. So without a prediction mechanism or a classification mechanism like this, what an anti-malware vendor would do is they can run their check against known malware. After that, they have to look for some other signals, either reports from users, or they just take a random sample of devices and try to analyze all the applications of the devices. So this is what we want to, this is the scenario that we want to target. So we did this by basically taking this malware and dividing it into 5 groups. The groups were divided so that each group infected roughly the same number of devices. And 4 of these groups stand in for known malware, and 1 group will stand in for unknown malware. So we will train the classifier based on this known malware, 4 sets of known malware, label them according to those 4 sets. And then if we can classify the set of devices, remaining set of devices with respect to this last set of malware, this unknown malware. And if you can do that well enough, then that would be would give us confidence that we are able to actually classify devices as either clean or potentially vulnerable. So we did this again separately for Mobile Sandbox and McAfee. So like I said, we had this malware divided into 5 groups, and then the devices are divided into 2 groups. One training set, which consists of the bulk of the devices, 80% of the clean devices, plus all the devices that are infected by this known malware, the 4 sets of malware packages that stand in for known malware. And the test set consists of 20% of the remaining clean devices, plus all the devices that are infected by this last set, this new set of malware. And the job was to train the classifier using this training set and see if we can predict, how well we can predict infection with respect to this last set, the new malware set. And the numbers we get are similar. So again, like the baseline will be something like 0.27%, but the precision with which we can predict is a little better. So it's not 10 times or 100 times, which would have been much more useful, but it's given that it comes cheaply, this might still be a useful tool in, that antivirus vendors can use. So we did a couple of variants of this. So this variant was assuming that all the new malware was not seen in the training set. The training set was labeled using the known malware, and we test against this new malware. But in reality, that might not be the case. Sometimes you might actually have a malware package in your training data, but you just didn't detect it as malware. So all those devices that had the undetected malware would have been classified as clean devices, and that would actually change the classifier because the classifier would mislearn. So we tried to model that by saying that we take the training set, we have 80% of all devices as the training set, and 20% of the remaining devices as the test set. And in the training set, if there was any device that had malware from this unknown malware set, we change the label to clean so that the classifier would learn the wrong thing. And that, of course, brings down the improvement, but it's still better than random classification. So it's still better than just picking a bunch of devices at random and checking to see how many of them are really infected. So finally, we had, so this was really sort of simulating what is old malware and new malware, but we actually had a real case of old and new, because in both datasets, the malware datasets that we used, we actually got two deliveries. So in the beginning, when we started the project sometime in March or April, we got one set of malware from each source. And then sometime later in October or November, we got an update with a bunch of new malware. So we tried this in this realistic scenario where we trained the devices using this first set that we got from March, labeled the devices using the first malware set, and then tried to predict if any of them would, if the classifier would actually identify devices that are infected with respect to the updates that we got later. And then this is in line with what we got before. So again, something like 4 or 5 times improvement. So what we haven't done here is these carrot records have timestamps. And currently, so far, we haven't paid attention to the timestamps. We take all the applications that are found on a device, and we treat them as one big pool. Even though over time, some packages are installed, and then some packages may be uninstalled, and so on. And we noticed, for example, that in our data set, 21 devices out of this 50,000 changed state. So they were uninfected in the beginning and then became infected at some point. None changed state in the other direction. So in all the cases, everything that infected stayed infected until the end of our data collection. But we only had a 6-month data collection period. So if this is the case, then it would be interesting to see. So what we have tested so far is, can we classify or can we detect infection based on previously undetected but currently present malware? we could try to extend this further and say, can we actually identify a device which is not infected yet? It doesn't have malware, neither known malware or known malware, but it's going to get malware down the line. And if we can predict that, that might have interesting use cases as well. So identifying vulnerable devices before they are infected. We haven't done this yet, and we don't know if this is true, but if we could do this, it will be this kind of minority report kind of thing. So the use case would be something like, imagine that you have an enterprise that had, I don't know, 100,000 employees, and Fraser was telling me this morning about sort of, earlier today about users who are sort of magnets for bad behavior. They don't know about hygiene, right? So an enterprise might want to give hygiene training about how to, don't go to a porn app store, or don't install things that are flashy or whatever. So they can do this training, but they have to, how do they focus this training? So they can't train all 100,000 users. Having something like this, if they could identify vulnerable devices, then they could focus training on those owners of those vulnerable devices as a way to sort of steer them away from getting infected. But we haven't done this, and this, as you can imagine, this can also lead to bad things. So maybe if your device is vulnerable, your enterprise fires you because you haven't been following corporate policies. Okay, so before I conclude, I just wanted to sort of summarize what we can do in the future. So we have done this with 6 months worth of data. So obviously we are still collecting data, so we could repeat this analysis sometime later, and that might lead us to better insights. We have to make use of these timestamps, which we are not right now. And the classification methods that we use, and neither I nor my students are machine learning experts, so we are using very simplistic classification techniques, and there might be better classification techniques that could give better results. So these are the things that we are trying to do right now. So the summary is that I think we have been able to measure that the malware infection rate in Android devices is actually very small. It's in the order of 0.2%, but it's smaller than pretty much every figure that antivirus companies themselves report, but it is significantly higher than the previous independent report, which used this indirect method, the talk that you heard in October from Patrick Traynor. We haven't found any strong correlation between battery life or number of applications, but we did find that this, looking at the set of applications that are used on a device, even though it's not an accurate predictor of an infection, it can be used to sort of narrow down the pool of devices to a set of vulnerable devices. And that can help in things like how do antivirus companies find previously unknown malware. Rather than doing a random selection, they could use this as a way to narrow down the pool of devices that they pay attention to. So we just published a research report. This is not published work because we just finished it. There's a research report in arXiv. Either you can go there or you can search for my name in arXiv and you'll find the report. And like I said, we haven't been doing malware research before, so if you look at this and have some insights or know of related work, please let me know. That would be very useful. So that's basically what I had planned to say.
Any questions? I should please repeat any questions.
Okay.
Otherwise it won't get recorded. Questions?
Ian.
So this CARrot application, does it report what applications are installed or what applications are running?
Running. So it actually walks through. The question was, does CARrot report applications that are installed or applications that are running on a device? And the answer is they actually report applications that are running because they walk through the process list periodically and report those applications that are running. And I don't know exactly how they measure the average battery life. That was not our concern. So those are the two things that they report.
So if there's malware on the device, but it's not running right now, it won't report?
No. So if malware is on the device and over time it never runs, then it won't get reported. But I would say that's actually acceptable malware if it never runs, or if it runs at some point later.
How often does Carrot sample?
I don't know the answer to that exactly. So what we have seen in our data set is for every device over the 6-month period, we get something like 10 to 50 samples. But I don't know exactly when, how they do this. So these guys who did the Carrot project also have a startup. And this is the reason why I don't know all the details. So they have a paper that's published in Census this year, and but I don't know about the front end code is public. So I suppose we can find out how often it reports. But the back end, the analysis that they do in the back end is not public. Yes.
So you mentioned that there was a graph of different antivirus companies.
Mm-hmm.
And there seemed to be a difference between PC and mobile malware. So can you comment on what's the difference between malware on PC and malware on mobile devices?
So,
why should there be executable infection and things like that?
Right.
Those companies that are just very specific. So
right. So the question is, I showed a graph that showed sort of market share as we measured for different malware tools, and there seemed to be a difference between sort of PC malware vendors and then mobile-only malware vendors. And the question is, what's the difference between PC malware and mobile malware? So I don't really know why some of the PC malware vendors don't show up prominently. Some others do. I think the second in the list was, if I remember right. So, for example, Avast and AVG, these are Norton. These are, of course, well-known PC vendors. But some others, like Kaspersky, is way down below, and FCQ is not even listed. So I don't know the reason for this. But I think there are some reasons, differences between mobile antivirus tools and PC antivirus tools. And one of them is, I think one of the reasons why infection rates are low on mobile devices is because of platform security, right? So mobile devices have a security architecture which can isolate between applications and so on. That also works against antivirus tools. So antivirus tools cannot do as much on mobile devices as they can do on PCs. On PCs, they can actually analyze every application coming in. They can instrument them before they do file access and things like that. On mobile devices, it seems what they do is really not much more than what we did, which is look for signature matches. But of course, this doesn't answer your question of why is there a market share difference. So there's no pattern. It's not the case that only mobile-only vendors are predominantly in the leading position here. But I don't know why some of them don't show up prominently.
initially when you started out, you said that the antivirus vendors, their numbers are like double digits, where in fact it's much, much lower. So can you tell, like, I mean, maybe they're not misleading us, they're just using a different way of measuring. What way of measuring are they?
Right, so the question is, initially I said that the infection rates reported by antivirus tools, antivirus vendors are higher than what we found out or what Patrick Rainer's group found out. So they're not double digits, they're still single digits. I think the highest was like 4% and Lookout was 2%. So this is still an order of magnitude higher than what we found and several orders of magnitude higher than what Patrick's group found. So I think I don't think, or there is no evidence that they are actually lying outright. So as you can see, even these two data sets that we saw didn't agree with what constitutes infection. And every package that we tried was not classified as malware by a majority of the packets. So it seems like they use different criteria. And these gray areas, like, what if there is something that is a monitoring application, some of them seem to count that as malware and others don't. So that might be the reason why some AV vendors have a higher rate, because they are more inclusive in what they label as malware. But what is remarkable is that antivirus vendors, you would expect that antivirus vendors would periodically report what is the infection rate. And this they don't seem to do. So these are like very rarely that you find. Every antivirus company has regular reports, annual reports, and quarterly reports, and so on about the state of the technology. But usually they talk about the number of different Android malware variants that they discovered has doubled in the past year, but not about infection rate. And I don't know why. I mean, you can speculate as well as I can. The other thing, again, you can speculate as well as I can, is there have been some accusations, but not proven, that some antivirus companies deliberately don't detect some malware. So that doesn't, again, explain why these estimates are higher, but that might explain the differences. So, for example, an antivirus vendor from a certain country seems to detect malware that originates from other countries rather than that particular country. And the accusations are that there have been other motivations than just technical. But yes.
So given that your numbers are 3 orders of magnitude or something higher than the Georgia Tech numbers,
Yeah.
so one thinks about why that would be the case.
Yes.
Rather than just the technique. So one is that perhaps you have false positives as a consequence of the reliance on the database, right? That's a possibility.
Mm-hmm.
Okay. So I was just trying to think about what other reasons there could be.
Right. So the question is, why is it that we have a significantly higher infection rate than the Georgia Tech numbers? So I think the primary reason probably is that their method was indirect, and their method was limited to US. So they had data from a US carrier and a US ISP. And I think from many of these antivirus vendor reports, it seems like the infection rates in the US are much lower than infection rates in, say, Russia and China. And for about Carrot users, we don't know anything about their demographics. Carrot, because of IRB regulations in Berkeley, they don't collect any data. So we know that they are spread around the world, but clearly not all of them are in the US. So that could be one reason. The second reason is that their method is based on DNS requests. So they look at known bad DNS requests. Not all malware makes DNS requests. I think a common variant of malware is something that uses this premium SMS. So they come with, they send, without the user knowing, they send SMS to premium numbers, and the attacker runs away with the money after that. So their technique will not detect this class of malware that doesn't make DNS requests. And then the third one is, like you said, we might have false positives, and I mean, they worked with a set of bad DNS names. And again, I would imagine that if there are different antivirus vendors have different lists of bad DNS names, that might also be a possibility.
Okay, we've unfortunately run out of time. If you have additional questions, Asokan will be meeting with CrySP students in the CrySP lab in about half an hour, so please stop by there. And yeah, let's take this house for one more time.
Thank you.